So this is the fourth video on chapter 10, and we will continue with examples on how to use the heat equation using the specific heat capacity. So we have this example too. A candy bar has 120 calories in one serving. A bomb calorimeter contains 700 grams of water at 25 degrees Celsius. When the candy bar is burned in the calorimeter, what would the final temperature of the water be? Assume complete transfer of heat from the candy bar to the water. So let's look at this schematic of bomb calorimeter here to the right. So nutritionists, to measure the amount of calorie contained in food, they use these kind of calorimeters. So the sample, the food sample would be in the center, and that's the yellow mass there in the crucible. And it's in a chamber that is called the still bomb, and that's the pink space there. And so you're burning the food to release the energy from the food, and then so the still bomb here will get warm and transfer the heat from the inside of the chamber to the outside, and it's surrounded by water. It's completely submerged. The water will absorb that heat. And if you know the mass of water, so you need to know the mass of water that is put in there, and you need to know the initial temperature of water. So that's why there is a thermometer there. There is a stirrer to homogenize the temperature of water. And by having all these data, the mass of water, the initial temperature of water, and as the food will burn, it will reach a maximal temperature. And so you record also that maximum temperature. And all of this will allow you to calculate the heat captured by the water, absorbed by the water. And because we assume complete transfer of the heat released by the still bomb to the water, that means it's the energy released by the food. So that's how nutritionists measure food calories. So notice how the still chamber needs to have an oxygen supply, because you cannot burn food or burn anything burn anything without oxygen. So that's why we have this oxygen supply to the still bomb. So here we can imagine that we have this candy bar placed into that still bomb, and then there is the ignition coil ready to ignite the food. And the oxygen is there to make this happen. And so we know the mass of water, it's 700 grams. So let's see what we have given here. We have the mass of water, 700 grams, the initial temperature of water, 25 degrees, and then the heat released by the candy bar that has been measured previously, 120 nutritional calories. Notice how the capital C tells you it's food calories or nutritional calories. And so what are we trying to find? We are trying to find the final temperature of water that would be measured when this candy bar was burned. So we will need to use the heat equation, that is Q equal ms delta T. And we need to understand here that the Q is the Q of the candy, so the heat or energy contained in the candy bar. The ms and delta T are all relating to water, because that's how you are able to measure the energy of the candy bar. So it's the mass of water, specific heat of water, and the temperature difference that water undergoes. So we need to rearrange this equation to find TF, the final temperature of water. So by dividing both sides of the equal sign by ms, you get ms cancelled out on the right side, and then on the left side you have Q of candy over ms. And that's equal to the delta T, Tf minus Ti. And we are looking for Tf. So we need to have it Tf by itself on the right. So we'll move the negative Ti to the left side of the equal sign, and that will become positive when it's on the right side. And so rearranging everything, we have Tf of water equals Q over ms plus temperature initial of water. So let's see now, can we plug in the values already? So it all depends on the specific heat capacity that we are using. Remember how food nutritional calories, one capital C calorie is equal to 1,000 lowercase c calories. And one lowercase c calorie is 4.184 joules. So we know the specific heat of water is equal to 4.184 joules per gram and per degree. And seeing that 1 calorie is 4.184 joules here, we can also write the specific heat of water as 1.00 calories per gram and per degree. In fact, the calorie was defined by being the amount of heat necessary to warm 1 gram of water by 1 degree Celsius. So that's why it's exact here, 1.00 for water in calorie per gram and per degree. So if we use that value of the specific heat, then we only need to change the nutritional calories to a lowercase c calories. So let's convert the 120 food calories into normal calories. So we start the calculation with 120 capital C calorie, and we will use 1 capital C calorie equals 1,000 calories as the conversion factor, written such that the capital C calories cancel, and then we have lowercase c calorie on top, and that's the unit we keep in the end, and we multiply 120 by 1,000, and that's 120,000 calories. We have 2 sig figs in 120 calories, right? The 0 is not significant because we do not see the decimal point. So we keep 2 sig figs, and we have 2 sig figs right there. So we have now our Q in calories. We have the specific heat of water in calorie per gram and per degree, and we have our degree Celsius. So we are ready to plug in the values in TF of water. So TF of water is Q of candy, so 120,000 calories over the mass of water is 700 grams, and multiplied by the specific heat of water in calories per gram and per degree, and that's 1.00. And then plus Ti of water, the initial temperature of water was 25 degrees Celsius. So you do the calculation, the division before you can add. So the intermediate answer for the division part is, so 171.428 degrees Celsius. And notice how it's degrees Celsius because the calories cancel, the grams cancel, and you're left with degrees Celsius. So it's indeed a temperature. It's actually a temperature difference here. And we add 25 degrees to that. Notice how we need to, so we do not round intermediate answer. So this first value here, 171.428, is not rounded. We need to estimate how many sig figs we keep because we have a multiplication division here. The 700 grams contains 3 sig figs. The 1.00 calories per gram and per degree, it's 3 sig figs as well. And we have 2 sig figs in the 12 or the 120,000 calories. So that's why the 7 is underlined to say that we need to keep 2 sig figs there. But now we are doing an addition and the rule is changing. It's the least precise digit that matters. And here between 25 precise to the degree or to the ones and 171 degrees, but actually precise to the tens, to this 7 here. So it's to the tens. So that means when you add them, so you keep everything, add them, and that's the calculator answer, 196.428. We need to keep it to the tens because the precision, the least precise digit was to the tens. And so when you run this to the 9 here, what comes after the 9 is a 6. So you need to run the 19, if you will, up to a 20. However, if you write 200, it's going to show only one significant figure. And we need 2 here because to the tens, because we have a number in the hundreds. So it's, translating into 2 sig figs. So we will need to use scientific notation to show 2 sig figs. And it's going to be 200 written in scientific notation with 1 0 significant. And it's going to be 2.0, 2 sig figs, times 10 to the second power, because we need to show that it's 200 degrees Celsius. So that's the final temperature of water in this example. Let's do a concept check now. And for this, you need to pause the video and try this on your own before you watch the answer. So we have 74.8 joules of heat is required to raise the temperature of 18.69 grams of silver from 10.0 degrees Celsius to 27.0 degrees Celsius. What is the specific heat capacity of silver in joules per gram and per degree Celsius? So let's gather all the information we have. We have 74.8 joules. That's the Q, the heat. We have the mass of silver, 18.69 grams. And we have a temperature going from 10 degrees to 27 degrees Celsius. What are we looking for? We are looking for the specific heat capacity of silver in joules per gram and per degree. So we will need to use the heat formula, the heat equation, which is Q equals ms delta T. And because we are looking for S, so we need to rearrange it so that we have S isolated. And that means you need to divide both sides of the equal sign by m delta T. And so S will be equal to Q over m delta T. Let's see now, can we plug in the values? We have heat in joules, mass in grams, degrees Celsius for the delta T. So that corresponds to all the units we need for the specific heat capacity, joules per gram and per degree. So we can plug in the values. Let's calculate S. It's Q over m delta T. Q is 74.8 joules. M is 18.69 grams. And delta T is 27.0 minus 10.0 degrees Celsius. Delta T is always Tf minus Ti, final temperature minus initial temperature. Here, because we have this subtraction to do, and the rule is different, so we need to do that first. We need to do what's in parentheses first, and we need to apply the rule that says to keep the least number of decimal places. And here, both numbers, both temperatures have 1 decimal place. So we will need to keep 1 decimal place. 27 minus 10 is 17. So it's 17.0 because we need to keep 1 decimal place. Now it becomes 3 sig figs. 17.0 is 3 sig figs. The 74.8 is 3 sig figs, and the 18.69 is 4 sig figs. So doing this calculation in the calculator, you get this calculator answer, 0.235420 joules per gram and per degree. So as we said, we have a minimum amount of sig figs of 3 from the joules and from the degrees Celsius. So we will need to keep 3 sig figs. So we keep the 0.2, 3, 5. What comes after the 5 is the 4, so we keep the 5 a 5. And so the final answer is 0.235 joules per gram and per degree Celsius. We keep 3 sig figs. And I can confirm from the values in the table we had in a previous video that this is indeed the specific heat capacity of silver in joules per gram and per degree Celsius.